Welcome to lesson 3.4, perpendicular lines. Hopefully in class, before you're doing this lesson, we looked at some examples of what happens when the transversal is perpendicular to at least one of the parallel lines, or possibly both. But if not, that's okay. So one of the first concepts, our main learning target anyhow, is to be able to prove and apply theorems about perpendicular lines. This first concept isn't directly related to this, but it is one of the things that we learn in lesson 3.4 that's going to be very relevant throughout the rest of our course in geometry, and that is that we have a distance between a point and a line. So if I'm me, you know me, I like to take as least steps, the very fewest possible steps in a proof to get to the end. Well, the same thing when I'm walking from a point to a line. If I have to go all the way around or take a long way to get there, I will. So, or I might walk a straight path there. But I don't want to go that far if I don't have to. So I'm going to go directly to the line as long as I don't have any obstacles in my way, directly to the line. Well, you should notice something about this line and the path that I would take. They are perpendicular. So the distance between the point and a line, or the most efficient, that's the key part, efficient distance, which they're not going to tell you that, is going to be the path perpendicular to that line. The path perpendicular to that line from our point. And that's actually the distance from a point to a line, not a line's a line, is the path that's perpendicular to that point. So when we see all these triangles, we're like, oh, look, they're asking us to name the shortest segment. Well, that's easy from point P. And then set up and solve an equation, or an inequality, rather, to solve for x. Well, that's the shortest distance from P to B is 5. So PB is the shortest distance, and PB is 5. Now an equation, looking in these triangles, we're supposed to set up, you might not be looking at these as triangles, but we will. If this is shortest, then this is longer. So this is longer than this path because it's not the most direct. Therefore, my equation would be x plus 3 has to be greater than 5. And so therefore, the value of x, if I take 3 away from both sides, has to be greater than 2. Try this for letter B. For letter B, you should have said that the shortest distance from point P to line AC is on that perpendicular path. So AP is the shortest path, and the distance from A to P is the expression x minus 5. To solve or to set up an equation, if this is the shortest path, then 12 has to be greater than that path, x minus 5. And so I'm going to add 5 to both sides, so I get 17 is greater than x, or converse, or actually using the symmetric property, x is less than 17. So there are my answers. Here's my answers for those. Actually, all of it is, because we also had to set up the equation. That was part of it as well. A perpendicular bisector. Later on, we're going to be writing equations of perpendicular bisectors. Actually, not too much later on, but we already know how to write equations of lines, so we'll be okay there. It means exactly what it says. It has two key words in its definition. The first one being perpendicular, meaning that the lines, or the segments in this case, intersect at right angles. And the second key vocabulary word being bisector, meaning that a segment was bisected. A segment was bisected. So I'm going to have line L, and I'm going to make it an L. They don't both have to be segments, but one of them does for it to be bisected. And I'm going to have AB be bisected. Well, line L is the perpendicular bisector. L is the perpendicular bisector of segment AB. What this means is two things. AB has been cut into two equal parts, or two congruent parts by the definition of bisector, and line L and AB, where they cross at 90-degree angles, or right angles, because they're perpendicular. So we're going to draw a picture for this and then try to solve the problem. It says BD is a perpendicular bisector to AC at point P. So AC is the segment that's being bisected, and they're forming a right angle because they're perpendicular. So I'm going to draw, here's A, here's C. BD doesn't have to be bisected. It's a line extending forever, so we don't know if this is the middle or rather at all where the line starts. Here's point P. I didn't draw this too well because AP and PC are supposed to be congruent. AP is that expression, so 12x minus 3/4. PC is that expression, 3x plus 51/4. That means this and this, because it's been bisected, are congruent. Now, if they'd given me the whole thing, then 2 times this would give me the whole thing, if you remember from Unit 1 of geometry. But since those are the two pieces that are congruent, we can actually set 12x minus 3/4 equal to 3x plus 51/4. To solve, I'm going to get rid of fractions right now by multiplying everything by the least common denominator, which in this case is 4. Multiplying my 12x by 4 gives me 48x. Multiplying 3/4 by 4 gives me -3. Multiplying 3x by 4 gives me 12x, and multiplying 51/4 by 4 gives me positive 51. So now I'm ready to solve. Just going to get my x's to one side by subtracting 12x from both. I now have 36x minus 3 equals 51. I'm going to add 3 to both sides. So 36x equals 54. Divide by 54 by 36. 9 goes into both, so that should be 6/4. It'll reduce further than that. Hold on. So 3/2. In terms of a fraction, the value of x is 3/2, or 1.5. Now let's double check what we were asked to solve for, because I didn't read that. They asked us to find, here it is, find AC. All right, so that means I have to put my 3/2, or 1.5, back in here. So I've got 12 times 3/2 minus 3/4, which is 17.25. That's the value of AP. Then I have 3 times 3/2 plus 51/4, also 17.25, so I know I did that right. 17.25 times 2, or add those two pieces together. The distance from A to P is 34.5. 34.5. The next problem says that GP and TY are perpendicular bisectors to each other. Well, that means that they're both perpendicular bisectors, which means they've both been bisected. It does not mean that all 4 pieces are equal, though. It means that this GP was bisected, so this is equal to this, and TY was bisected, so that is equal to that. It also means that these are all right angles, so if I had a variable expression for that, I'd set it equal to 90. We're supposed to find the values of x and y, so my equation will be, one of my equations will be these equal pieces. 5x plus 3y equals 18. My other equation is for TB and BY. 4x minus 2y equals 10. I'll come back and solve this system at the end if you want to keep watching the video, but we're only supposed to find the values of x and y. So at the end of this video, I will come back and let me make a note to myself to solve B, for those of you who want to see it worked out. We do have 2 theorems coming up, 341, 342, and 343. That's what they're labeled as in our textbook. But I am not going to I'm not going to require you to memorize them by number. In fact, we're rarely going to use them in proof. We most frequently use our alternate interior angles, alternate exterior angles, same side interior angle theorems, and corresponding angles postulate and their converses a lot in proofs. But these particular theorems that we're going to write down come from our textbook. The first one, 341, says if two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. This is something that's really, really basic, and we could actually do a simple proof of. Basically, you have this picture right here. You have line L. So you've got this angle and this angle making our linear pair, and the angles are congruent. So the only thing that we can say, well, for them to be congruent, since they have to add to 180, that means that they both have to be 90. Since they're both 90, that means that these lines have to be perpendicular. That's all that theorem says. So you may want to pause the video and take a moment to write that down. If you wanted to write the gist of it, this is the part you would write. Two intersecting lines form a linear pair of, the key part there is congruent angles. That implies, or rather, if that, then the lines are perpendicular. Remember, this implies is the same as if the first part, then the second. So that could save you in some writing. The next theorem, 342, says if a transversal is perpendicular to one of two parallel lines. So the given includes these parallel lines, okay? And we have this right angle here because the transversal is perpendicular to one of them. Well, then it should come pretty easily that it's going to be perpendicular to the other line. Think about it. This angle is 90 degrees, so are all the ones around it. Looking at the parallel lines, you're either looking at this, which is alternate exterior with the right angle, or this one right here where the arrow is right now. That's corresponding with the one that's already marked a right angle. Or since all of these are right angle, you could even have alternate interior, any of the angle pairs. Even same side interior, which you're like, well, those aren't going to be congruent. In this case, they will be, but they'll also add to 180 because 90 plus 90 is 180. So the conclusion is that all the angles down here, since all the angles down here are also right angles, this line also has to be perpendicular to Q. So if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. This is the conclusion box right here in terms of our hypothesis, and then over here is the conclusion. Take a moment to pause the video if you need to write that down. 343, we're not going to memorize them by their theorem number. There's no point. They're numbered differently in every different textbook that anyone writes. So here we are. If two coplanar lines are perpendicular to the same line, then the two lines are parallel to each other. So this says two lines perpendicular, same line, implies two lines are parallel. By the way, coplanar is important because it's very possible to have a three-dimensional shape that has right angles, and then the two lines aren't parallel. They may actually be skew. And we can show you what that looks like in class if you want to ask about it. But here, they didn't tell us the lines were parallel. This is, hey, there's a right angle and there's a right angle. Well, it's very easy for us to use converse of corresponding angles postulate to say the lines are parallel. They're saying you don't need to do that. You can just cite this theorem. But we're not really giving this theorem a name, so we're not going to worry about it too much. Pause the video if you do need to write any of those down, or you can go to page 173 of the online geometry textbook to grab those. All right. We're supposed to write a two-column proof. Some of you are like, oh, I see that shape. That shape's a rectangle, Mr. Ritter. So I know these facts about a rectangle. It very well is a rectangle, and there's things we can prove about it, but we need to follow our steps one at a time. So we have all of this given information, and I normally like to put it all in one line. I'm going to be lazy and do that again. But I'm going to highlight in a different color which ones we're talking about as we go through this proof. The first thing that we're given is that the lines AD and BC are parallel. What does that give us? Well, if you remember, when we're told things are parallel, we're allowed to use the corresponding angles postulate. But if we're not given parallel lines, we'd better not use that postulate. Well, I'm going to look at those parallel lines in just one of these transversals, this one right here, and possibly even this one right here. So looking at this one, that means that I need additional points. If I really want to do this, I need additional points. So I'm going to call this, there's a couple different ways to do this. I'm going to call this point E. And that's all I should really need. Actually, we're not even going to use that. We'll just use this. Let's look at this transversal right here. We've got the parallel lines, and that is perpendicular. Well, then guess what this angle right here has to be? We'll call this point F. It has to be 90. So what I'm going to say, since they're parallel and we have this part that AD is perpendicular to, it says AD is perpendicular to AB, that gave us this right angle. So from that statement, I'm going to write that angle DAB is a right angle by definition of perpendicular. And because it's a right angle, that means, oh, actually, we did prove something earlier, so I'm just going to leave it there. That would mean that it is 90 degrees by definition of right angle. But remember, we've proven right angle congruence theorem, which says that all right angles are congruent. So we used that actually a while ago. We're actually going to start using that theorem here. Since these are congruent, that means that angle, because the lines are parallel, that means that angle DAB is congruent to angle CBF. CBF. So because they're corresponding with the parallel lines, and this being the transversal, this angle is also a right angle. And I'm going to say that that is corresponding angles postulate. I guess we probably do need equations here, but I'm just going to go. This line right here means the measure of angle DAB equals 90 degrees by definition of right angle. Well, if that's the case and these are congruent, this is a little out of order, the measure of angle DAB will have to equal the measure of angle CBF by definition of congruent. And then using substitution, CBF has to be 90 degrees. I could have used the theorems above to do this proof to make it a lot shorter, but we're not going to memorize those, so I don't really see the point in that. So now I've got this, which since that's 90 degrees, that means that angle CBF is a right angle. Okay, I don't think we're going to have many more lines after this, but we'll have to go to the right of the page. So that is definition of right angle, which is in your flipper. If you see an angle is 90 degrees, you can say it's a right angle by definition of right angle. If you're told it's a right angle, you can say it's 90 degrees by definition of right angle. Also, if you see that lines are perpendicular, you can say that they form a right angle by definition of perpendicular. And if they form a right angle, then we can say that the lines are perpendicular by definition of perpendicular. So what are we trying to prove? We're trying to prove AB and BC are parallel. All right, I'm going to come over here. I've got, now I have that this is perpendicular, and I was given this one was perpendicular, or that they were right angles. So I'm using the fact that those are perpendicular. I'm going to write my line 8. That angle DCB, this one right here, is a right angle by definition of perpendicular, because that's how I knew it's a right angle, because they were perpendicular. Now, we have this as a right angle, and we just established that CBF is a right angle, which means that those angles are congruent. angle CBF and DCB are congruent. This is a new justification. We haven't used this one before. We're saying that because they're both right angles. And the right angles theorem says that all right angles are congruent. So since they're both right angles, we can say they're congruent by the right angle theorem. It's actually called the right angle congruence theorem. I abbreviate it right angle theorem, though. And now, our last line, what are we trying to prove? A, B, and DC are parallel. So we're trying to prove AB and DC are parallel. And those angles are alternate interior, and we've shown they're congruent. So our last line is AB is parallel to DC by converse of alternate interior angles theorem. This one was a little bit of a tough proof, but hopefully you could see where we're going from step to step. Might have not had the whole picture overall. Let's take a quick look at angle, or at letter B in just a second. I have not done this proof yet, but we're going to look at it and figure it out as we go. We were given EFH, or no, sorry, what is it? EHF, that's this angle, and HFG are congruent. Well, you should already see something based on that given statement. Here's where it might help to separate our givens, so I'm going to do that. There's our first given. What type of angles are EHF and HFG? You should see the letter Z. So because those are congruent, that tells us something about the lines. That tells us that this line and this line have to be parallel. Since those lines are congruent and we know their relationship is that they're supposed to be, we can say EH and FG are parallel by one of the converse theorems. So this is how we use the converses in proofs. Converse of alternate interior angles theorem. They gave us that the alternate interior angles were congruent, so we're concluding the lines are parallel by converse of alternate interior angles theorem. Whenever we say lines are parallel, this is what we use. So now I've established that. That's great. They also tell us that FG and GH are perpendicular. Here's FG and GH, and those are given as perpendicular. Well, that is another given. I'll put it here. What does that mean? That means that we have right angles. That means that angle FGH is a right angle by definition of perpendicular. What does that mean? Right, since it's a right angle, that means that the measure of angle FGH is 90 degrees by definition of right angle. So this is just following some of the statements and reasons given in our flipper. If we're told perpendicular, we can conclude right angles. Definition of perpendicular. If we're told right angles, we can conclude 90 degrees by definition of right angle. So I now know that this is 90 degrees, and I'm trying to prove EH and GH are congruent, are perpendicular. So I'm going to make a letter over here. Let's call that letter D, because here's G, and that's 90 degrees. This, since we now have established that these lines are parallel, and this is our transversal between the two parallel lines, if this is 90 degrees, this has to be, wait, no, we're trying to prove those are parallel. We're trying to prove EH and FG. No, we're not. We're trying to prove EH and GH are perpendicular, so that's okay. We already did establish those lines were parallel. So I can now put a right angle here. Well, at least I know that those two angles are congruent. So that's going to be my next line. I know that because I see the letter F. So angle FGH is congruent to angle EHD. And I know that because they're corresponding angles, so that's the corresponding angles postulate. Since they're congruent, I can say the measure of angle F, well, we already know FGH is 90. We can say the measure of angle FGH equals the measure of angle EHD because they're congruent, so the reason is definition of congruence. Because they're equal in measure and FGH is 90 degrees, notice FGH could work as a connector, so you could use transitive property of equality. I'm going to use substitution. Measure EHD is 90 degrees by substitution. Lines 5 and 7. I'm almost done. Angle EHD, I have 2 more lines after this, is a right angle by definition of right angle. No, actually 1 more line after this. They're 90 degrees, so that means this is a right angle, which we already knew, but we had to put it in our proof. And now, since it's a right angle, that means that this, well, is EH, and this is HG. They have to be perpendicular. So since it's a right angle, EH has to be perpendicular to HG by the definition of perpendicular. There is an alternate way, to do this proof using some of the theorems above, but I'm not going to have you memorize those 3 theorems because we don't use them frequently. So that's why I actually did the math and the algebra to show from step to step. This concludes the video notes for 3-4. You'll be able to do some practice problems, hopefully like these, and involving perpendicular bisectors. And then hopefully you can also use our converse theorems in proofs, and the definition of perpendicular, definition of right angle in proofs as well. Have a great day.